Welcome to this neural network programming series. In this episode, we will see how we can experiment with large numbers of hyperparameter values easily while still keeping our training loop and our results organized.
Hey, by the way, do you know that DEEPLIZARD has a vlog? If you want to connect with us in a totally different light, then come check out the vlog and say hi. Link in the description. All right, let's get to it.
When we left off with our training loop a couple of episodes back, we built out quite a lot of functionality that allowed us to experiment with many different parameters and values, and we also made the calls needed inside our training loop to get our results out and into TensorBoard. All of this work has helped, but our training loop is pretty crowded now. In this episode, we're going to clean it up and set the stage for more experimentation by using the Run Builder class that we built last time and by building a new class called Run Manager. This work will take our training loop from looking like this, what we see here, to looking like this. Much simpler and easier to extend and easier to reason about. Our goal here is to be able to add parameters and values at the top and have the values tested or tried during multiple training runs. For example, in this case, we are saying that we want to use two parameters, learning rate and batch size. And for the batch size, we want to try two different values. This gives us a total of 2 training runs. Both runs will have the same learning rate, while the batch sizes will vary between the 2 runs. At the bottom, we'd like to see and be able to compare the results of both of these runs. And by extension, we'd like to be able to add any number of parameters and any number of parameter values and still be able to reason about the results and the code that makes up the training loop. To do this, we need to build 2 new classes. We built the first class called Run Builder in the last episode. It's being used here at the top. Now we need to build this Run Manager class that will allow us to manage each run inside our run loop. The Run Manager instance will allow us to pull out a lot of these tedious TensorBoard calls and allow us to add additional functionality as well. All of this without cluttering our training loop further. We'll see that as our number of parameters and runs get larger, even TensorBoard will start to break down as a viable solution for reviewing our results. But this will be okay because of the added functionality that we'll do ourselves inside the Run Manager. The Run Manager will be invoked at different stages inside each of our runs. We'll have calls at the start and end of both the run and the epoch phases. We'll also have calls to track the loss and the number of correct predictions inside each epoch. Finally, at the end, we'll save the run results to disk. So let's see how to build this Run Manager class. First, we declare the class using the class keyword. Next, we define the class constructor. For now, we won't take any arguments in the constructor. We'll just define some attributes that will enable us to keep track of data across runs and across epochs. We'll track the number of epochs, the running loss for an epoch, the correct number of predictions for an epoch, and the start time of an epoch. And we're going to do this for each epoch. Remember we saw that the Run Manager class has 2 methods with epoch in the name. We have begin epoch and end epoch. These 2 methods will allow us to manage these values across the epoch lifecycle. Now, next, we have some attributes for the runs. We have an attribute called run params. This is the run definition in terms of the run parameters. Its value will be one of the runs that's returned from our Run Builder class. Next, we have attributes to track the run count and the run data. The run count gives us the run number, and the run data is a list that we'll use to keep track of the parameter values and the results of each epoch. And this will be done, of course, for each run. And so we'll see that we add a value to this list for every epoch. Then we have the run start time, which will be used to calculate the run duration. All right, next we'll save the network and the data loader that are being used for the run, as well as a summary writer that we can use to save data for TensorBoard.
Whoa. Like Jinkies. Do you smell that? There's something that doesn't smell right about this code. Have you heard of code smells before? Have you smelled them? A code smell is a term used to describe a condition where something about the code in front of our eyes doesn't seem right. It's like a gut feeling for software developers. A code smell doesn't mean that something is definitely wrong. A code smell does not mean the code is incorrect. It just means that there is likely a better way. In this case, the code smell is the fact that we have several variable names that have a prefix. The use of the prefix here indicates that the variables somehow belong together. Anytime we see this, we need to be thinking about removing these prefixes. Data that belongs together should be together. This is done by encapsulating the data inside of a class. After all, if the data belongs together, then object-oriented programming languages give us the ability to express this fact using classes.
It's fine to leave this code for now, but later we might want to refactor this code by doing what is referred to as extracting a class. Extracting a class is a refactoring technique where we remove these prefixes and create a class called epoch that will have these as attributes. The new epoch class would have an attribute for count, loss, numCorrect, and start time. Then we would replace these class variables for the run manager with an instance of the new epoch class. We might even change the count variable inside the epoch class to have a more intuitive name, say like epoch number or epoch ID. The reason we can leave this in for now is because refactoring is an iterative process, and this is our first iteration. Actually, what we are doing now by building this run manager class is indeed extracting a class from our main training loop program. The code smell that we are addressing in this case is the fact that our training loop was starting to become pretty cluttered and beginning to appear overly complex. When we write a main program and then refactor it, we can think of this as creating layers of abstraction that make the main program more and more readable and easier to understand. Each part of the program should be very easy to understand in its own right. When we extract code into its own class or method, we are creating additional layers of abstraction. And if we want to understand the implementation details for any of the layers, we dive in, so to speak. In an iterative way, we can think of starting with one single program and then later extracting the code that creates deeper and deeper layers. This process can be viewed as kind of an unfolding or branching tree-like structure. Anyway, let's go ahead and look at the first method of the class, which extracts the code needed to begin a run. First, we capture the start time for the run. Then we save the passed-in parameters and increment the run count by 1. After this, we save our network and our data loader. And then we initialize the summary writer for TensorBoard. Notice how we are passing our run as the comment argument to the summary writer. This will allow us to uniquely identify our run inside TensorBoard. And its value will automatically update anytime we add or remove parameters to our parameter list. Alright, next we have some TensorBoard calls that we made in our training loop before. These calls add our network and a single batch of images to TensorBoard. When we end a run, all we have to do is close the TensorBoard handle and set the epoch count back to 0 to be ready for the next run. And that's the entirety of the implementation for the end run method. For starting an epoch, we first save the start time, then we increment the epoch count by 1, and set the epoch loss and epoch number correct to 0. Now let's look at where the bulk of the action occurs, which is when we end an epoch. We start by calculating the epoch duration and the run duration. Since we are at the end of an epoch, the epoch duration is final. However, the run duration here represents the running time of the current run. This value will keep running until the run ends. However, we'll still save it here with each epoch. Next, we compute the epoch loss and accuracy. And we do this relative to the size of our training set. Then we pass both of these values to TensorBoard. Next, we pass our network's weights and gradient values to TensorBoard just like we did before. And now we're ready for what's new in terms of processing here. This is the part we'll be adding to give us additional insight when we perform large numbers of runs. We're going to save all of the data ourselves so we can analyze it outside of TensorBoard. Here, we are building a dictionary that contains the keys and values we care about from our run. We add in the run count, the epoch count, the loss, the accuracy, the epoch duration, and the run duration. Then, we iterate over the keys and values inside our run parameters, adding them to the results dictionary. This will allow us to see the parameters that are associated with the performance results. This is important because we can query and see what results match up with which parameters. Finally, we append the results to the run data list. Once the data is added to the list, we turn the list into a pandas data frame so we can have formatted output. The next two lines here are specific to Jupyter Notebook. We clear the current output and display a new data frame. This will ensure that our output is updated opposed to being appended each time. Alright, that ends an epoch. One thing you may be wondering is about the epoch loss and the epoch num correct values. Exactly how are they updated in this process? Well, we have two methods just below for this. We have a method called trackLoss and a method called trackNumCorrect. These methods are called inside the training loop after each batch. The loss is passed into the trackLoss method, and the predictions and label tensors are passed into the trackNumCorrect method. To calculate the number of correct predictions, we're using the same getNumCorrect function that we defined in previous episodes. The difference here is that the function is now encapsulated inside our run manager class. We have an underscore at the front of it to indicate that it is sort of like a private method, not really intended to be used by outside callers. The underscore doesn't prevent outside callers from making calls, but it does signal to the caller that this method is mainly used internally to the class. Lastly, we have a method called save that saves the run data in two formats, JSON and CSV. The output goes to disk and makes it available for other apps to consume. For example, we could open the CSV file in Excel, or we could even build our own even better TensorBoard with the JSON data. And that's it. Let's define our training set and we'll see this code in action.
Whoa. Like Jinkies. I'm still catching whiffs off of some of this code. Did you yourself detect any code smells? If you also smelled things from this class implementation that could be better, please put your code smells in the comment section of this video.
Alright, so here we've ran our program with two different parameters and two different values for the batch size, and this produces two separate runs. Now we can see this if we look down at the output in the run column. We can see that we have 5 epochs for the first run and then 5 epochs for the second run. And then if we look over in the batch size column, we can see the batch size was changing in between runs. Now furthermore, we can see our loss and our accuracy and then epoch duration, run duration. Alright, so that's the setup, but now what I want to do is show you how easily we can add additional parameters and test out different ideas. So suppose that we know that the data loader has a shuffle parameter and that we can actually shuffle our batch data. What this setup allows us to do is go ahead and add that parameter and then test it across all parameter possibilities. So in this case, we would test the shuffling with a batch size of 1000 and a batch size of 2000, and we would test the values of the shuffle being on and off. So we'd get to see the results for when shuffling is on and when shuffling is off. So let me show you what we do to add shuffling. We just come up here and we add a shuffle parameter. And then we add values. If we only add one value, that's just going to add this value across the current two runs. But if we add two values, that's going to cause this process to actually test all value combinations. So in this case, we're going to have 4 total runs this time. Now to get access to these shuffle parameters inside our run loop, we just come down here to the data loader where we're going to use the value, and we say we want the shuffle to be equal to the run shuffle value. So when we get the run back from the run builder, it's going to have now a shuffle value or a value for shuffle that we can access via the run. So we just type run.shuffle and we will get back that value. Now let's run this updated code and see what happens. All right, now we have the output for all 4 of these runs, and we can compare the results across the 4 runs. So we can compare our loss, our accuracy, our epoch duration, our run duration, and then we can do this with respect to the last 3 columns, which are our run parameters: learn rate, batch size, and shuffle. We can see that the learning rate was the same across all of the runs. However, the batch size varied. We have 2 groups. We had 2 runs that used 1000 as the batch size parameter value, and then we had another group of 2 runs that used 2000 for this parameter. And then we varied the shuffle parameter across each of these. So for the 1000 group, we have true for a shuffle value, and we have false. And then for the group of 2000 values for the batch size, we have true and we have false. And one thing that you'll notice is that all we had to do was add shuffle at the top, access the shuffle value inside the run loop, and then the shuffle value showed up inside of our output results here. And all of this was automatic, and it works no matter how many parameter or parameter values we add. In addition to this, both the results CSV and the results.json file were written to disk. So we could, for example, take the CSV file and we could open this inside of Excel, and then we could sort different columns and do any kind of querying that Excel would allow us to do. Also, I just want to show you the results.json file, which has each epoch for each run. We have a JSON object here with all of our data. This would be easily consumable by any application that wanted to display or query this data. If you haven't already, be sure to check out DEEPLIZARD.com, where there's blog posts for each episode. There's even quizzes that you can use to test your understanding of the content. If you don't know already, DeepLizard also has a blog. The link is in the description, so you can come over and say hello. And don't forget about the DeepLizard HiveMind, where you can get exclusive perks and rewards. Thanks for contributing to Collective Intelligence. I'll see you in the next one.
Whoa. Like Jinkies. Hello. Don't mind me. I've just been here refactoring code and pondering this question. Oh. You are wondering what the question is. Well, the question is this. What does it feel like to be wrong? Maybe we might describe it as feeling bad. Or, maybe we might describe it as embarrassing, or humiliating. Well, no. Actually, this is not the way it feels to be wrong. These are the feelings we feel after we know we are wrong, in which case we are no longer wrong anymore. From this fact, we can deduce what it actually feels like to be wrong. That is, what it feels like to be wrong before we realize it, is what it feels like to be right.